Hi everyone, thanks for coming to my talk. And for today we're going to talk about one interesting data-driven optimization for actually all good native languages like Rust and some numbers. So by applying only this optimization, we can optimize our applications and libraries, like many applications, some of them are in Rust and a lot of Rust libraries, by these numbers. These numbers are pretty impressive, especially if you care about performance. So we're at Rustikon Conference, so we care, at least somehow, about performance. So let's begin. A few words about me. I came to Rust from the C++ world. I wasted several years with C++, with the C++ committee. I was working on compile time stuff, like const expr, if you know about it. I was hacking LLVM in different parts, here and there, like static analyzer and middle-end optimizations for LLVM. And spent last 2 years with PGO on a daily basis, optimizing a lot of different applications with PGO. Most of them are written in Rust. And regarding my current role, I'm a CTO in a cybersec company. Nothing too interesting, but cybersecurity and Rust are good friends. So let's talk about compilation. Actually, there are two major ways how to compile our programs. The first one is the head of time model. It's a native model for Rust. So we have our usual CI/CD pipeline, DCS, source code is coming to a compiler, and the result is a binary, like in machine code, and this binary is deployed to a target machine. The second model is a just-in-time model. It's not a usual model for Rust, but it's possible, but not usual. The same CI/CD pipeline, the same source code, compiler, and as a result, instead of a machine code, we have some kind of bytecode. And this bytecode is deployed to a target machine, and on a target machine, this code is executed by usually like a VM or just-in-time compiler and compiled just-in-time during the execution. So modern compilers, good modern compilers are optimization compilers, and they perform a lot of different optimizations, like inlining, loop roll unrolling, devirtualization, link time optimization, if you care about it, and many other things. And we don't care about details about any of these optimizations. We care about how they can be improved. And most of these optimizations can be improved a lot, the quality of this optimization, by providing some statistics about how your application is executed in runtime, which branches are executed, how frequently they are executed in practice, and so on. For example, that's a screenshot from LLVM. According to the file name, it's inline code, something about inlining. And here we see some interesting defaults for inliner, like inline threshold, hint threshold, and so on. That's LLVM details, and these constants, they are added to the LLVM by some experts. And unfortunately, these constants are not good enough for all applications. And optimization, inline optimization, one of the most important optimization in the compiler, can suffer from this suboptimality. And the solution for this is profile guide optimization, because in just-in-time world, we can collect runtime statistics on a target machine because we have a compiler, but in a ahead-of-time world, we don't have a compiler on a target machine. We only have our binary, usually. So what the profile guide optimization is? So let's collect somehow runtime statistics about our application. This statistics is called a PGO profile. Pass this profile to the compiler and use the information from this profile during the compilation phase. That's it. Nothing difficult. For example, we have a simple function, and this function is compiled in the release mode, opt level 2 or 3. I don't care. So pretty straightforward assembly code. If you're careful enough, you can see that the second and third branch are reordered. I don't know the exact reason why, because Clang don't do it. doesn't do it. But anyway, that's not important stuff. On the right side, we have the same code, but it's optimized by PGO, and we trained our PGO on the input, where the vast majority of inputs were numbers 322. So here is the first difference. At first, this branch is moved to the beginning of the function because it's executed more frequently, so we can move to the beginning of the function. And secondly, we also move the return statement to the beginning of the function because it improves instruction cache locality. So your CPU L1 instruction cache will be better in practice. And the rest of the function is pretty the same. So, about PGO kinds. Actually, there are different PGO kinds, like the instrumentation one, it's the default one for the majority of compilers. The sampling PGO, the most sophisticated one, but with some caveats. And actually, there are many different flavors and combinations of PGO where you can tweak some constants like context-sensitive intermediate representation PGO. We're just doing instrumentation PGO after the inlining phase, temporal PGO from meta for improving startup times. There is a CSS PGO, context-sensitive sampling PGO, no HTML PGO, fortunately. And there are many RFCs about some combinations. So how does instrumentation PGO work? So you need to compile your application in the instrumentation phase. At first, run the instrument application on your typical workload, somewhere on your typical workload, like a training workload, collect PGO profiles, recompile your application once again, and that's it. Pretty simple. Another example, another simple function in the middle, once again, release mode. And on the right, this function is compiled in the release mode, but this enabled PGO instrumentation. So the first difference we see an additional counter in keyword PTR. It's a counter which is automatically inserted by a compiler to the function. And each time when the function is executed, this counter is increased by 1. And by default, at the end of your program, at the exit, all these counters from all your program are dumped to a disk. It could be modified. You can dump to a memory, but it's tricky stuff. And the default default name for PGO profile will be default.profro. That's LLVM details, and that's it. So, unfortunately, instrumentation PGO has some caveats. At first, you need to compile your application at least twice. Once for instrumentation phase and another one for the actual optimization phase. And if your application is pretty large, your CI won't be happy. Second one, the instrumentation binary is larger because of the additional amount of instructions are inserted into your binary. For most of us, it's not critical, but for embedded guys, it could be a question. And an instrumented binary is slower because an additional amount of instructions is executed in practice. So let's talk about some numbers. So here we see some applications. Actually, only one of this application is written in Rust. It's a vector. But the situation is pretty the same for C, C++, and Rust applications in practice because they share the same ecosystem. We are talking about LLVM stuff. So in practice, we see that the binary increase is not a critical thing for us here. Like up to 2x increase, so we can live with it because disk space is pretty cheap. However, the binary slowdown can be a tricky thing because in practice it is unpredictable. It depends on the structure of your application. It depends on the target workload of your application, how many instrumented branches, for example, are executed, and so on. And for example, for the ClickHouse, we see a pretty ridiculous slowdown. That's not a mistake. These numbers are confirmed because a lot of counters were inserted to really hot loops in ClickHouse. And that's why the performance was affected so much. And we see that the numbers are pretty random here. So Google found all these problems, I guess, 15 years ago, but Google cares about performance, and they decided to implement another PGO. And this PGO is called sampling PGO. So it should resolve at least some problems of instrumentation. So how does it work? At first, you need to run your usual version, your usual application. Almost usual, but OK, some tricky details. Instead of collecting runtime statistics from built-in counters, you can try to use an external profiler, for example, Linux perf or Intel tune. And you can collect it externally by sampling your application with some frequency and collecting, for example, currently executed stack traces. Recompile your application once again with this runtime information, and the rest pretty the same. Unfortunately, sampling PGO also has caveats. The first one is called branch stack sampling feature. It's a hardware feature that allows to the external profilers collect more precise runtime statistics about your application in a more efficient way. Unfortunately, availability of this feature is pretty interesting. Like Intel and every hardware vendor has a different name. For example, Intel, last branch record, AMD, branch sampling, ARM, several versions of this, like branch record buffer extension from the latest ARM, and some core side features, but never worked with it from Android ecosystem. RISC-V, control transfer records. And availability of them could be a problem. For example, at home, I have a PC based on Ryzen 9 from Zen 3 generation, and according to the documentation, it should support BRS, but there is a tricky detail. Zen 3 supports BRS only for server versions of CPUs, like Threadrippers. But I have Ryzen desktop, so unfortunately I cannot test sampling PGO with BRS enabled. And another limitation is virtualization, because as far as I know, BSS feature is not properly virtualized by different hypervisors. If you know anything more about it, please tell me, because I don't know. And another thing is limited tooling support. So why do we need an additional tooling? Your compiler cannot work directly with statistics from your external profiler, from Linux perf or Intel vTune or whatever you want to use. You need some kind of converter. And Google, and there are several of them, Google implemented a Google Auto Video projects. Unfortunately, it has a lot of bugs. For example, it depends on LLVM internal things, but it's an out of 3 project, so expect a lot of build errors with the latest LLVM and so on. They can be fixed, but Google actually doesn't care much about accepting an external pull request, so that's it. Luckily, as far as I know, the project soon would be merged into LLVM, so at least build issues would be resolved. Another project is a part of LLVM. It's called LLVM ProfGen, and that's like a state-of-the-art thing to work with profiles, but unfortunately it works only with BSS profiles. So if you collected runtime statistics by an external profiler without BSS support, LLVM ProfGen doesn't work in practice. And I reported it to the upstream, and they don't care about it. So they support only BSS. That's it. So let's compare instrumentation and sampling. At first, instrumentation, once again, according to different benchmarks also from Google, allows to achieve better optimization. According to Google results, like sampling PGO has from 80 to 90% of efficiency compared to instrumentation. So if you want to squeeze as much as possible performance, please keep it in mind. Sampling has far less runtime overhead. Actually, that was the only reason why sampling PGO was implemented. For example, 2% of overhead compared to plus infinity instrumentation. Remember the ClickHouse case. And you can tweak this amount of overhead by tweaking the sampling frequency in practice. So if you don't want to hurt your production workload much, if you decided to collect PGO profiles directly from production, so you can just reduce the sampling frequency, and that's it. If you want to get more precise profiles, improve frequency and measure the overhead in practice. And instrumentation has far better operating system and tooling support. For example, it's easier to implement instrumentation PGO at first. It's an important thing if you implement compiler. And another thing that sampling PGO is most features are contributed to sampling PGO by large corporations, and the aim for them to optimize their server fleets, and server fleets are Linux-based. So actually no one cares about Windows platform regarding sampling PGO, unfortunately, even Microsoft. Yes. And let's talk about common PGO traps and mitigations for them. At first, PGO can optimize some scenarios and at the same time pessimize other, like reduce performance. So actually that's an obvious thing, because if you remember the reshuffle of branches case, if one branch is moved to the beginning, other branch are suffering. So that's it. So if you at this situation, you can try to build different versions of your applications, like one versions per workload. For example, we have 2 web servers, and we see 2 dedicated workloads for them. Just build 2 binaries and deploy them and reroute traffic between them, something like that. Just an example. And if it's not possible for some reason, like CI overhead and so on, you can try to collect different PGO profiles and merge them into the one generic profile. Probably it will be less efficient at each workload, but in general you will still get some performance improvement. There is a ready-to-use tooling in LLVM, so we can use it for PGO profiles pretty easy. PGO build is not reproducible. So with the PGO optimized build, we have an additional input, a PGO profile. So reproducibility is a hot topic, especially for Linux-based operating system maintainers and so on. So how you can resolve it? You can just commit your PGO profiles into some storage like a VCS, something like that, and use this profile during each build. If your build is already reproducible and you use the same PGO profile during each build, you should be fine. So your build will remain reproducible. There is another thing, is collecting the same PGO profile in a reproducible way. It's a problem because in general, you need to get somehow a reproducible execution of your application. And in general case, it's not a resolved problem in practice, like different threads, multi-threading, timing-based things, different branches, and so on. So when you saved your PGO profiles to some storage, you can get another problem, like your PGO profile can become outdated. So because your application is not a dead application, new code is added, existing code is changed, and so on. And in a few weeks, or in a few months, your PGO profile will be outdated. At least the new code will not be PGO optimized, and at worst, your existing code will be pessimized from performance perspective due to the incorrect PGO profile. The solution, just regenerate PGO profiles with some frequency. Which frequency? It depends on your application. It depends how many code is added during each sprint, for example, something like that. You need to figure out it on your own. And in some cases, PGO doesn't help to optimize your application, you have a good training workload, and you still cannot get a performance improvement. So I met several applications like that. For example, FFmpeg, and for example, from the Rust world, that's a ripgrep. That's a pretty awesome version of grep, the only awesome version of grep, to be honest. And you cannot optimize them more because people already optimize it a lot by hands. So for such projects, please don't waste your time, at least for now, but maybe later new code will be added and this code will be less optimized. So maybe in a few months, a year or so, PGO will help, but not now. So don't give up if it doesn't work for some application now. Maybe it will work later. So let's talk about a bit about PGO profile collection. There are different strategies to do it, but please don't collect it from unit tests. Because by unit tests, usually the main reason for unit tests to test your application or libraries or whatever you want in all cases, and most of these cases usually are corner cases, but we are not optimizing for corner cases. We're optimizing for real workload. So please don't use unit tests. From benchmarks, it depends. It depends on how similar your benchmark suite is to the actual target workload. For example, for databases, we have like ClickBench for a lab database or TPC-H. They are pretty good to be a training workload for a general case. For other domains, it could be a problem if your benchmarks are not good enough. From manually crafted training scenario, that's a good option. That's actually how Rustc is optimized by PGO. For example, for a compiler, the target workload is compiling a program. So we can write a bash script where you just run an instrumental version of Rustc to compile a small program and use this profile to get an optimized version of Rustc, and that's it. It's a pretty good option, but please be careful because your bash scenario could become outdated, so you need to somehow keep track that your target workload is the same, to this training scenario. And from production, it's actually probably the greatest option because it won't become outdated and so on. But please be careful because in this case, highly likely, you will not be able to use instrumentation PGO because of overhead. Highly likely because in some cases actually you can do it. But in most of the cases, sampling PGO will be your friend here. So in general, it depends, as usual. So what about PGO support in Rust compilers? Let's talk about Rust, actually. Rustc supports both instrumentation and sampling PGO in practice. The same for the Rustikon compiler, that's a certified version of Rustc, because it's the same compiler actually. About other compilers, there is no support. It will not be support in the near future. GCCRS, because they have another things to do right now. Rustc, because no one cares about it, and our Rust compilers, because if any, and actually I don't know about them, it would be pretty tough to implement PGO at the same level as Rustc because of Rustc reuses a lot of LLVM infrastructure for PGO. So let's talk about PGO issues in the Rustc. At first, documentation. Documentation is pretty thin in Rustc, and it refers to the Clang documentation. Clang documentation is a big documentation about PGO. Unfortunately, you cannot reuse all things from the Clang documentation for the Rustc, and you need to know which things you can reuse and which things you cannot reuse. I know. Unfortunately, if you're a new PGO newbie, it could be a trap for you. Another thing, no documentation for PGO, like a PGO-related intrinsics. For example, you can dump PGO profiles instead of a disk to a memory, for example, if you don't have a disk or read-only stuff. And you can do it. There are LLVM things you can use from Rust, but fortunately they are not documented at all. And no information about many other practical PGO nuances. For example, how to optimize this PGO multilingual application. For example, Rust plus C++. it would be a tricky thing to do, trust me. And unfortunately missing some most advanced PGO modes. They are not so important in practice, but if you want to squeeze some percent or two, so please use C++. And some bugs, they're not critical, and the most critical one when you couldn't use LTO and PGO at the same time was fixed at the current Rust nightly. So if you met some error like LVM broke in model, something like that, please just update your Rust compiler and that's it. What about support in other languages? If you want to get some inspiration from other ecosystems and so on, so at first please take a look at C because they have the maturest existing implementation for PGO in the world, because Google and the Meta, they have a lot of money, and they contributed to the these implementations a lot. About other implementations, like I guess I would say level a bit worse and sometimes much worse than Rustc. But you can get some inspiration to talk with other people from different ecosystems and so on. How to apply PGO in practice? There is an extension, Cargo PGO, implemented by Jakub Kobzol-Biranek from the Rustc. That's a guy who optimized Rustc with PGO and other stuff. Please use it. And this Cargo PGO, your workload for generic cases will be the same, like a few commands, and that's it. Actually, that's how I optimized most of the Rust applications with PGO. That's it. So please use it. If you want to talk about like enterprise-ish PGO, we want to do it continuously, because for large enterprises we have an additional bunch of problems like collect PGO profiles continuously, optimize services with PGO continuously, and do it for the large service fleets. For example, we have thousands or tens of thousands of services. We cannot do it manually, so we need some platform. Yandex open sourced the only open source solution right now for doing it. It's called Yandex Perforator because, like, you know, it does brrr for compilers, and that's it. So please use it. It's cluster-wide tested for large scales and so on. There are some ideas to implement it based on our open source solutions. Unfortunately, no progress yet for like a year or so on. About PGO state across Rust applications, unfortunately, almost no Rust applications except Rustc support optimizing PGO, and the same thing for the recipes in operating systems, because maintainers don't want to do it because they have a lot of things to do else. And you can some inspiration. You can try to find some good recipes from performance-oriented operating systems like CacheOS. They're especially crazy about PGO, and that's it. So if you want to use a Rust-based application with PGO, you need to recompile it. So some few examples. As you see, the situation is pretty sad, especially like for some for projects from some speakers, like a Limbo. Interesting thing, that's a Ferrocin compiler, because it's downstream compiler of Rustc, but Rustc supports PGO, but Ferrocin doesn't. It's due to some certification complications from PGO, so it could be a bit more difficult to get certification done properly. That's the official answer from Ferrocin support. So good candidates for applying PGO on actually any large application, compiler, databases, different parishes, operating systems, and so on. I have benchmarks for all of that. And optimization roadmap. Please opt level 3. Before PGO, please enable LTO, because it will be much easier to do. Only after that, enable PGO. Instrumentation by default, because it will be easier to do it in most cases. Sampling for some, if you know what you do. And more advanced things like LVM bolt, application-specific operating system, and so on. Maybe machine learning stuff for compilers. LVM has support for that too. And not today, maybe next time, because I'm running out of time. So regarding some helpful links, I have 15 seconds. So if you There is a repository, my repository, awesome PGO. So if you want to find any information about PGO, like benchmarks, a lot of pieces of advice and so on, please go to the awesome PGO. Please read the Rustc documentation and LLVM Discord. That's a place where you can ask a lot of questions from LLVM developers about PGO nuances and so on. And that's it for today. Thank you.